Okay, welcome. Today is Tuesday, January the 5th. Spain Park AP Chemistry. If you're enjoying these exciting videos, please feel free to subscribe to my channel. I'm shooting for 100, you know? So I'm at 60 something. All right, so we started off working problem number 27 on the sheet that I have posted. Just kind of as a practice and try and see where we can do. So on that one, you're going to have a coffee cup calorimeter. A coffee cup calorimeter is nothing more than a beaker with a styrofoam cup in it with some water, and that just acts like an insulator, and we assume there's no heat loss to the surrounding. So anything lost by the metal is gained by the water. So when you go through and look, it says that we have a 28.2 gram sample of nickel. So 28.2 grams of nickel. The specific heat of the nickel is what we're looking for. And the delta T is going to always be final minus initial, and it ends at 25 degrees minus the initial of 99.8 degrees Celsius. That's going to equal the mass of the water, 150 grams, times the specific heat, times the T final again, 25 degrees, minus the 23.5 degrees. So this time the math is a little bit easier. We don't have to use distributive property. This one turns out to be, and we have to put our negative sign. I always forget my negative sign right there. This one turns out to be negative 74.8 degrees Celsius. This one turns out to be 1.5 degrees Celsius. But then I'm assuming you can do the simple math. When you do all of that, the specific heat of the nickel turns out to equal, what did we say it was? 0.446. And the units that would be joules per gram degrees Celsius. So now we want to take it to another, just a different variance, and so we want to look at problem number 23. And try to see if you can do, pause the video, see if you can do number 23, and then come back once you're finished, and I'll show you how to go over it. So are you all done? Now 23 only has one substance. It's not putting a metal into water. It's not something getting hot, something else getting cold. It's just how much heat does it take to raise one piece of metal a certain number of degrees. And so that's always just going to mean it's just going to be Q equals MCAT. Since it's asking for heat, which variable are we looking for? Joules, which is which letter? Q up here in our equation, right? And so we're looking for Q. So Q is equal to the mass. What the mass of the aluminum is 850 grams. The specific heat of the aluminum is given as 0.9 joules per gram degrees Celsius. And the desired temperature change is from 22.8 to 94.6. So final minus initial, 94.6 minus 22.8. Do what?
After you minus that, it's 71.8.
So this is 71.8 degrees Celsius. Okay, so now we just multiply all that out, 850 times 0.9 times 71.8, and we end up getting Q is equal to 54,927, which is how many kilojoules? To 3 sig figs. 54.9 kilojoules. So we need to be able to just make sure we can go back and forth between joules and kilojoules. That's really easy, just move the decimal 3 places. But now part B says, calculate the molar heat capacity. Okay? The molar heat capacity, well, what do we know? What do we do? How do we find that? Good question, huh? Anybody?
Replace the 850 grams with the molar mass of aluminum.
Okay, but yes, in a sense, but not completely right. Okay, we know that the specific heat, C, this little c, is equal to 0.9 joules per gram degrees Celsius. We want to convert that to how many joules per mole degrees Celsius. So what do I need to get rid of? Grams, and change it to moles, which we use the molar mass. So we'll say 0.9 joules per gram degrees Celsius times the molar mass of nickel, 58 something, 58.69.
Is aluminum that we're working with? Which one?
Aluminum, okay, so we're at 26.98. That helps. 26.98. I want grams is on the bottom, so I want grams on top, moles on the bottom, so grams cancel. That gives me what number?
24.28.
24.28, and that's going to be joules per mole degrees Celsius.
I know that the original equation is like Q loss, or Q loss equals negative.
Negative Q gain, but that's only when you're putting something hot into something cold. One thing's losing, one thing's gaining. And this one is strictly saying how much energy needs to be added, so everything's positive, because we're adding the heat. If the temperature were going down, the sign would be determined by this, because we'd have a negative temperature, so we'd have a negative Q. Okay, so the way you differentiate is we only have one object there being heated versus this problem that was over here. One was hot, one was cold, and they were combining them together. That's how you know Q loss equals Q gained here versus just Q equals MCAT here. All right? Let's just continue on and just do number 24, and then we'll move on to a new topic. Number 24. Those of you watching at home on this one, you'll get to fast forward through this where you pause the video, work on it, and then fast forward till we go over the answer. First off, does everybody know what is graphite composed of? Pure carbon. Okay, so whenever you're having to deal with this, it's just carbon. Okay, if you're still working on parts B and C, just keep working, but kind of listen with one ear. If we want to raise the temperature of 1 mole of graphite, how do I set that up? MCAT, okay, but so Q is equal to what? What mass do I use? 1 mole, but
It's 12.01 grams.
12.01 grams, okay? Grams per 1 mole times joules, 0.71 joules per gram degree Celsius times 1 degree Celsius. So degrees Celsius cancel, your grams cancel, and you get how many joules it takes per 1 mole. And that turns out to equal 12 times 0.7, 84 something, right? 8.53 joules. Okay? So we could have just used this and done the exact same thing and just multiplied this by 12 to change from because the amount of energy it takes to raise 1 mole, 1 degree, that's your molar heat capacity. So just like we just did on the previous problem, you could have just multiplied this by 12.01 and that gets you your molar heat capacity. Now if it was something other than 1 degree, then we'd have to do the whole thing, okay? So now B says raise the temperature of 850 grams. So again, this one's just Q is equal to 150 grams times the 0.71 joules per gram degrees Celsius. And then we have to get how much is, raise it by 150 degrees. I can't see it, there it is. And that,
It's 850 grams.
well, yeah, that's what I said 850 and I wrote 150. 850 grams times 0.71 times 150 and all that equals a lot. Say it loud enough for me to hear. 90,525. Okay, that's joules, so to 3 sig figs, how many kilojoules is that gonna be? 90.5 kilojoules, and on both cases, we're increasing the temperature, so everything's positive on Q. And then the last one, C, is just gonna do kilograms, so it's gonna 75 kilograms is how many grams? 75,000 grams, again, times specific heat, not 4.71 joules per gram degrees Celsius. Now, does it matter that it's in Kelvin? Because when you subtract, it's gonna be the same. Delta T is the same when you go 0 to 100 degrees for a freezing point to boiling point of water is a change of 100 degrees. You add 273 to both, 273 to 373, the change is still 100 because you added 273 to both. So it doesn't matter, as long as it's delta T, you can use Celsius or Kelvin. Ideal gas law, PV equals nRT, where it's not delta T, it's just T, you have to use Kelvin. Okay? So, what's the delta T end up being on this one when you subtract them? 54, okay? So that all equals 500 joules, which is going to be 2875.5 kilojoules. All right, so that's just using Q equals MCAT. Notice it's all one thing. You're not putting something hot into something cold. Hot and cold, you use Q laws equals Q gain. You can either find the specific heat of the metal or you can find the final temperature of the solution. You need to be able to do those types of problems. Also encourage you to go back and look at our heating curve where it's the heat, temperature versus heat. I talked about that a lot in the video yesterday, and so you need to make sure you know how to do those problems as well when we have phase changes, okay? All right. I do want to remind you all that you have a hard copy and an electronic copy of your textbook, so you can feel free to read some of that, which is chapter 5, which is what we're doing right now. We're going to combine chapter 5 and 19. I don't know why they always separate them, but they go hand in hand, so we're going to do those together. All right, so that's all been about just the differences between kinetic and potential energy. How do things absorb energy? How can we measure the energy? And so now we want to look at energy can be transferred. And this is going to be D in the outline that was started.